Okay, we're going to be looking at 4.6, which is talking about congruence and right triangles. So we know how to tell whether or not any other triangles are congruent. Is there a specific way to tell whether or not right triangles are congruent besides SSS, SAS, ASA, and AAS? So first of all, I want us to look at the following two triangles. They are very obviously not congruent, but I want you to look at the information that we have in these. So in each of these, we have two pairs of sides that are congruent. We have a side of 4 and a side of 5. And then we've got two angles that are not congruent. Now these are non-included angles. So we know, we've talked about this before, how this congruence does not work. If the angle is not included, it's not going to work. And this is a really good example of why it won't work. Okay, these again, these are two triangles that are very obviously not congruent, yet have two pairs of sides and an angle. The only difference here is the angle is not included, so it completely messes up the two triangles. But this will work for right triangles, except for we won't call it this, we'll call it a different theorem. Before we get into that though, I want to look at a right triangle and look at the different parts, some of which you probably already know, but I want to refresh your memory on that a little bit. So we know that a right triangle is just a triangle with a right angle, right? Just one right angle. And if you think about it, a triangle can only have one right angle. Because if it had two, that'd be 90 plus 90. 90 plus 90 is 180. But all three angles have to add to 180. So you can't have two 90-degree angles or there would be nothing left for the third. So it's just a triangle with one right angle. If a triangle ever has one right angle, you automatically know it's right, which we'll be using a little bit today in our reasoning. And then there's some parts of a triangle. The longest leg of the triangle, this one right here, which is across from that right angle, is called your hypotenuse. Your hypotenuse is always opposite the right angle. Always, always, always. So that is the hypotenuse of our right triangle. And then the other two sides of that right triangle are called your legs. So here AC is the hypotenuse. AB and BC are both legs of the right triangle. That's really important that you know how to tell the difference in those things. So finally, we have the hypotenuse leg theorem, which really is the same thing as SSA, only for right triangles. Okay, we're not going to call it SSA though. We'll call it HL. If you're going to abbreviate it that way. So what the HL theorem tells us is that if the hypotenuse and leg of one right triangle are congruent to the hypotenuse and leg of the other right triangle, then the two triangles have to be congruent. So here you can look at the following picture. We have hypotenuse PR is congruent to hypotenuse XZ, and also we have that side, or leg PQ, is congruent to leg XY. Since these are both right triangles by the HL theorem, I know that they have to be congruent to one another. All right, and there is a proof in your book if you want to look at that. If you're curious to why this works and why it doesn't work for other triangles per se, you can look. But I want to look at something real quick. Let's just call this side length X and this side length Y. And since the red ones are congruent, let's call them, let's call them both C, because they're the same C, they're congruent to one another. And let's call the blue sides both A. So I don't know if you remember something, you've probably been exposed to it before, called the Pythagorean theorem. What it says is that the two legs of a right triangle squared equal the hypotenuse of the triangle squared. So I want to look at this real quick. If we were to use the Pythagorean theorem for this triangle, we would have a squared plus x squared equals c squared. If we were to use the Pythagorean theorem for this one, we would have a squared plus y squared equals c squared. Now, if I were to solve this one for x squared, it would be c squared minus a squared. If I were to solve this for y squared, it would equal c squared minus a squared. So these two things equal, they both equal c squared minus a squared, so therefore x has to equal y. So that's kind of an explanation, a proof, just using the Pythagorean theorem. You can see that those things are going to have to be equal to one another as well. So then the triangles would be equal by side, side, side. So just want to take you through that a little bit. There is a formal proof in your book if you want to look at it a different way. It is not using the Pythagorean theorem. Okay, so let's look at an example of this. So let's look at the following. Angle PRS and angle RPQ are right angles. And we know that SP is congruent to QR. So first of all, and this may seem silly to you, but if it tells you that they're right angles, what do we know about those two triangles? Well, we know they're right triangles, right? So we know that triangle PRS and triangle RPQ are right. It told us the angles were right, so therefore we know the triangles are right. And that would just be your definition of a right triangle. A triangle with one right angle is a right triangle. Okay, so we've got that. So we're setting ourselves up to use HL theorem because now we know it's right triangles. Now we know that SP is congruent to QR. Those are our hypotenuse. That's the hypotenuse of each triangle. And so now we just need a leg to be able to say that the triangles are congruent. The only leg we have here is PR. PR is in both triangles, so we know that PR is congruent to itself by the reflexive property. So therefore, we know that the triangles are congruent. Triangle PRS, PRS is congruent to triangle RPQ by hypotenuse leg. And that would be your proof. So kind of easy when you have right triangles because we know we're going to use a hypotenuse leg. So you're just setting yourself up. You want to determine that the hypotenuse are congruent and also the legs are. So that's it for today. What we're going to look at tomorrow is proofs involving the hypotenuse leg theorem. See you then.